Before I get into when Gauss's law can be applied in cases of cylindrical symmetry, let me show you when you cannot use it. If you can see the end of a rod, then you cannot use Gauss's law. The reason for that is it no longer possesses the symmetry known as cylindrical symmetry. If this rod is charged uniformly or non-uniformly, it doesn't matter. But even if it's charged uniformly, you won't have cylindrical symmetry because of the nature of the field at the corner point. Far away from the endpoints, you could have cylindrical symmetry in the field, but because of this, it gets spoiled. So certainly you cannot use Gauss's law for cases where you can see one end of the rod, or for finite rods. You have to use Gauss's law only if the rod is infinite in both directions. So that's the limitation of Gauss's law. It's always true. Gauss's law is always true. Let's recall what the law of Gauss says. It says that the enclosed flux, which is given by the oriented double integral of the electric field dotted with the area vector at every point on the surface S, known as Gaussian surface, that quantity, which is called the electric flux, phi E closed, is equal to the enclosed charge by that Gaussian surface, whatever charge is enclosed, divided by epsilon naught. Basically, Gauss's law says if you don't have a charge that's enclosed, then the flux must be zero. But if the flux is not zero, then there must be some net charge enclosed. It does not tell you really much about the electric field. So the Gauss's law is always true. You can still use Gauss's law for this surface, and you will get an answer in accordance with this equation. But can you do anything with it? Can you find the electric field at every point? That's the question. Is Gauss's law true? Is never the question. Is Gauss's law useful? Is always the question. Gauss's law is always true, but in this case, it's not useful. You can really not do much with it than to say that the flux equals the enclosed charge over epsilon naught and then move on. Well, we want to use Gauss's law to predict something about the electric field. So in the previous video, I showed you how to use Gauss's law to find the electric field everywhere in a spherical charge distribution. Now, if you tried that directly by integration, you would be spending a very long time doing it, and you may also get the wrong result, whereas Gauss's law gives the answer in 2 or 3 steps. So we are going to try to do something similar here. Now, what kind of Gaussian surfaces can we draw? Now, this is a case where you can use Gauss's law because it does have cylindrical symmetry. I have a infinite charge, all plus charges, spread in a line with some linear charge density, which I'll call lambda naught. Lambda naught is charge per unit length, so the units of lambda naught are going to be in coulombs per meter. So that's got a uniform charge density lambda naught, and we have to find the electric field everywhere. Now, how to choose the Gaussian surface? A particularly bad choice would be something like this. If I chose the Gaussian surface to be not centered around the charge distribution, well, Gauss's law, as I said, is always true for any Gaussian surface. In this case, you're going to get the flux equals this enclosed charge enclosed by this length. So basically, your charge enclosed is going to be lambda naught times L. So the flux is definitely lambda naught L over epsilon naught. So I've solved the problem. I found the flux, but I found nothing else because the electric field at a point very far away from the rod, and that's the furthest it gets, is going to be smaller than the electric field at a point that is closer to the charged line. So you're really not going to be able to break down this integral any further into electric field and area. So our aim is always to split this up somehow into electric field and area, and so we can find electric field. So that's a poor choice of a Gaussian surface. What would a good choice be? Obviously one that's symmetric. So let's take a charged line, and this time I'll draw it by a solid line, and it's got a charge density lambda naught throughout. The Gaussian surface I'm going to choose is a sensible one, so I center it around the charge line. Now Gaussian surfaces are imaginary surfaces, so you don't have to get too hung up about their dimensions as long as you tell everyone what it is. So radius r and the length L. So what we're going to do is we're going to let the radius r expand to infinity while keeping length L fixed. Let's try writing out the flux integral, the left hand side, for each of these sides of the Gaussian surface S. It has three sides. One is the left side, the other is the right side, and the curved side. Before we do that, let's draw some electric field vectors on each of these sides. So I have here, the electric field is going to look like this, and the area vector on this side is going to be some, I'll call this dA curved surface, dAc. On the right side, I'm going to get dA right. On the left side, dA left. Okay. The electric field vectors on the left side are going to be some bigger electric field E. On the right side, some bigger electric field because it's closer to the line. And I can also go ahead and write some vectors on this side, if you will. So that's also dAr, and the electric field here would be like that. And I can draw a dA curved on this side and the electric field on that side, E, is the same size as this, and so on. So you don't want to write too many of these, just write a few to convey the idea that there is some cylindrical symmetry. So the left hand side of Gauss's law is the same for all problems with cylindrical symmetry. Let's see how we can reduce the flux integral. The oriented closed double integral over the Gaussian surface known as S, E dot dA, is going to be equal to the open surface integral over the left side, E dot dA left, plus the curved surface, E dot dA curved, plus the integral over the right surface, E dot dA right. Splitting up the integral into three surface contributions is what's happening here. Observe though that on the left side the angle between E and dA, and on the right side the angle between E and dA is 90 degrees. Now the dot product of two vectors which are perpendicular to each other is 0. So I'll put a 0 through the dot to convey that what 0 is the cosine 90 that comes from the dot product. So I only have one term left, and on the curved surface E and dA are parallel, so you have a cosine 0 degrees there. So let me write this out. This is going to be the double integral over just the curved surface, E times dA curved times cosine 0 degrees. Now you have a really nice situation. The electric field on the curved surface, because we did not take a Wacko surface like that, but took a symmetric surface like this, the electric field on the curved surface is going to be the same in magnitude throughout. So I can take it outside the integral sign, writing E of r as I do so, to convey that it depends only on the variable r and not on the variable theta or the variable z. I should remind you that in cylindrical coordinates we have the cylindrical coordinate system, r hat, the angle theta hat, and the axial z hat. So it's a three-dimensional coordinate system. So then I have the integral over the curved surface, dA curved. Now at this point, if you're a calculus hound, you can go and do the double integral. But most people already know these things from high school. The surface area of a cylinder is just the circumference of the circle times the length. So think of a toilet paper or a paper towel core, the brown core that's left over after you finish the roll. That roll will have a radius r, so the surface area, just that brown part, is going to be 2 pi r times L. So I can just write this out. E of r times 2 pi r times L. Done. I have done the left hand side, and it's the same for all problems. With cylindrical symmetry. The right hand side, as I've already mentioned, is just a charge enclosed divided by epsilon naught, and the charge enclosed is lambda naught times the length enclosed by the Gaussian surface, and the length enclosed is L. So the right hand side is very trivial in this case. Let me write it out. Q enclosed over epsilon naught equals lambda naught times L over epsilon naught, and I'm done. The Gauss law says the left hand side must equal the right hand side, so I get E of r times 2 pi r L must equal lambda naught times L over epsilon naught. The L's cancel out, which it had better cancel out because the length of the Gaussian surface is a figment of your imagination. It should not show up in the final answer. So E of r is equal to lambda naught divided by 2 pi r epsilon naught. This is the same result that we got with much agony when we did the whole thing by integration. If you recall, one of the videos of last week was to find this infinite line electric field in several steps. I first did it for a finite segment, and then I took the segment to infinity, and then I got this result. It was the end of a long video, and this is just quite easy. Now, if you don't have a uniform charge, what else can you have? Well, the one thing you can have is a cylindrical distribution of charge that is also uniform. Or it could be some function of r. So even though I'm drawing a finite cylinder, imagine the cylinder goes on forever. And let's assume that I have a charge distribution given by rho as a function of r. Rho meaning charge coulombs per meter cubed. Okay, and let's say the size of the cylinder is given to us. It's some size A. We want to find the electric field distribution everywhere, inside and outside. How would you proceed? You start out the same way. You start out by drawing a axial line in the middle, in reference to which you can draw two Gaussian surfaces, one inside and the other outside. Both these Gaussian surfaces can have different lengths and different radii, but just for the sake of simplicity, I'll take them to be the same length. And the radius label, even though the radius is obviously different, I'll keep the same radius label r for them. You're going to have the same type of picture here, so I won't draw it. E and dA for both inside and outside are going to look just like that, so I won't draw it. And the left hand side will also come out to be exactly the same, so I won't worry about that. I'll just focus on the right hand side. On the right hand side, we have a cylindrical symmetry situation, so we have to worry about the volume element in cylindrical symmetry. That paper towel core example comes back here. If you have a cylinder with a very thin amount of material, how much volume is there? So let's call the thickness dr and the radius of that cylinder, let's call it r. So the amount of material you have, dV, is just going to be 2 pi r times L times dr, surface area times the thickness. Done. Now if you multiply this by rho, you're going to get the charge enclosed, and if you integrate it, you're going to get the charge enclosed. So let's call this the Gaussian cylinder S1, and this is the Gaussian cylinder S2. Let's try to find the charge enclosed in S1 and in S2. So the charge enclosed Q is going to be the integral from 0 to r, rho as a function of r, times dV, which is 2 pi r L dr. And whatever the function rho I give you, you put it in there and you evaluate this. For S2, let's call this Q as a function of R. For S2, the charge enclosed is just going to be Q as a function of A, because you're going to go all the way from 0 to A and then stop there. Beyond that, there is no charge enclosed. Let's evaluate these for the case of the constant charge density, rho of R equals rho naught, just for kicks. So Q of R will then be, I can take the rho naught outside because it's a constant, so I get 2 pi R L, 2 pi rho naught L, and then I have integral R dr, which is R squared over 2. So the 2's cancel out, and I have that. Outside, I'm going to get Q of A, which is precisely pi rho naught L A squared, because I've put R equals A. Now I can set the left-hand side of Gauss's law equal to the right-hand side of Gauss's law, and I can find the electric field throughout in this particular example of a uniformly charged cylinder. So let me do that. So this is the uniformly charged cylinder case. The electric field E times 2 pi R L for the Gaussian surface S1 is equal to the charge enclosed, which is pi times rho naught L R squared divided by epsilon naught. You observe that one of the R factors cancels and the electric field is proportional to R. For S2, E times 2 pi R L is equal to some constant, which is pi rho naught L A squared. The L's cancel too, divided by epsilon naught, and the electric field here is 1 over R. So basically the electric field outside this uniform distribution behaves just like a line charge, and inside it behaves like a linear function. So if I quickly plotted this, I would get the electric field magnitude to look like this. It would go up, and then outside it would die off as a line charge. So that's a line decay, and this is just a 1 R growth.